So hello, we'll be answering a frame question that's targeted for UCO civil engineering students in first year. Now, for this question, my approach would slightly differ from the lecturer, but it works for all frame cases. However, this will change in year two, and you'll be taught something else differently. But yeah, so part A of the question is quite simple, and I'm assuming most of you guys will know how to do it, but let's do it anyway. So it tells you to work out the reaction forces at the support. So the reaction forces at the support will be at this place. There's no other places where there's supports, so we basically have to work out three forces here because it's a fixed end. So fixed end would mean a reaction force vertically, reaction force horizontally, and a moment there. Now I'm gonna call these this place A. Yep. And I'm basically going to divide it into a few reaction forces. So we have a reaction force that's going upwards, call it AY. A reaction force that's going this way, let's say, call it AX. And a reaction force that's going this way, let's call it AM. Just this is a moment, no, but it's reaction. Call it AM for M symbolizing for the moments. Now, if you take if you do the sum of, actually wait, before we do that, let's give a sign convention, otherwise to keep everything else consistent. So I'm gonna treat up as positive. I'm going to treat this way as negative, and I want to treat clockwise as positive. Now this is very important. If your sign convention may differ according to your lecturer, however, if you indicate your sign convention here, then they wouldn't penalize you unless they say otherwise in my lectures or whatever. But let's go on. So I'm going to do sum of forces in the y component is equal to 0. Now as you can see here, there is a 2 kilonewton per meter load, uniform load that's acting here, and that's the only vertical load that's been applied in the system, and that would obviously help us work out what AY is, because AY at the moment is currently unknown. So since we're saying AY is acting vertically upwards, we'll have AY minus 2 times by 4. Yep, it's times by 4 to make it into kilonewtons. So that's going to be equal to 0. So AY is going to be equal to minus 2 times 4 is 8. So it's simply going to be 8 kilonewtons. And let's do sum of fx is equal to 0. So this is the same thing. So AX, I'm just going to go a bit faster with this. AX is just going to be equal to 8 kilonewtons because of this. If you do sum of the horizontally, where x, yeah, so this is the x coordinate, just in case one of you guys gets confused. X, y. Yeah, this corresponds to the sign convention. Now, I'm just going to write it down here so I can save some space, and while keeping the diagram close. AY is going to be equal to, what do you say, 8 kilonewtons. That's right, kilonewtons. And AX is going to be equal to 8 kilonewtons. Okay, so I'm just going to rub this out. Okay, so now I'm going to work out what AM is. So sum of moments sum of moments at A is equal to 0. So that means AM is going to be equal to the moment induced from the uniform load and the moment induced from the point load. So AM here is going anti-clockwise, But if you was to put your hand where the fixed joint is and see where this load is, where the uniform load is taking you, the uniform load would, if you was to imagine that A was a pin and then you was to use that uniform load, it will make it go clockwise. And similarly, the point load, the 8 kilonewtons, would also be making it go clockwise. If you assume that A is a pin and then apply that load, both of these loads make it go clockwise. So AM is going to be equal to 2 kilonewtons, 2 kilonewtons per meter times by 4 times by where it's acting, which is going to be half of that beam. It's going to be 2, so half of 4 is 2, and we plus 8 times by 6 minus 1.5. Now this is getting a bit confusing, so let's write that out. So it's going to be 8, it's going to times by 6 minus 1.5. Now if you was to do that in your calculator, you get 52 kilonewtons meter. Don't forget the units. Okay, so now this is the slightly interesting part, like it's the slightly different part. So what I do is I cut it into segments, but it's going to be continuous segments. You'll understand what that phrase means as I go ahead in this video. So first of all, I'm going to consider this segment. So if I consider this segment, yeah, I'm going to have, I'm going to have the load here, which is going to be 8 kilonewtons. We'll be having a load here, 8 kilonewtons, and I'm going to have a moment here which is 52 kilonewtons meter. Now I've defined positive to be clockwise, so that means my moment here, I'm going to give it a clockwise moment just to keep consistent. Now it's asking you in part B to find out the bending moment diagram for all of this. So I'm going to get an equation for this part of the beam, then this part of the beam, and this part of the beam. So essentially I'm going to get a equation once you've crossed the different corners of the frame, and this would give you the bending moment diagram for this this diagram. So we'll have this, so that means, so taking moments, let's call this point A. So taking moments at point lowercase a, so it's slightly different. Taking moments from A, so M is going to be equal to 52 kilonewtons, because this one's going anti-clockwise and M is going clockwise, so if you point the other side positive, 52 kilonewtons. Now, oh wait, sorry, this cut where I did it is at an not an arbitrary length, but at a random segment. So it could have been there, could have been there, could have been there. So I'm going to give it a value of X. Yep. So it's cut around X. So it will apply to all of this side, all of this part of the frame. Okay. So that means, since that 8 kilonewtons acting through this part of the frame, it's not going to contribute in changing the moment of this. However, this 8 kilonewtons, I might just denote it here, this 8 kilonewtons will. So we're going to, it's going to influence the moment. So this one's going to be simply 8 times by X. Now, since this is making it go clockwise, and we want an equation for M, and we put, if we was putting the other side, it'd be minus 8x. So this is your first equation for this part of the beam. Now we're going to concentrate on this part of the beam. Yep. And this is where you might see a slight difference in your lecturer is working out to my working out. Now, I might just write actually, yeah, so let's do this. Okay, so now I'm going to do this part here. So I'm going to kind of continue on. X. 8 kilonewtons. Yep, and you have a uniform load here. Now, this time, let's make the moment the same. So this is also going to be positive, going clockwise. And it will always be clockwise. Yep, so denote as M. Let's call this B. So, okay. So the sum of moments about B is going to be equal to 0, correct? As it usually is, because it's static. So M, this M, is going to be equal to, now this is going clockwise, and this is going anti-clockwise, so that 52 must be positive. Going opposites. That 8 kilonewtons. Now, this 8 kilonewtons, regardless of how much you cut into the top beam, it will always have a moment of 8 kilonewtons times by this length. And since this length will always be 6 meters, because we're making cuts along this part of the beam, then it will always be 8 times 6. So it won't have to do anything to do with X. So it would be 52 minus 8x. Now the reason why it's minus 8x is because this is making it go clockwise, and M is also going clockwise. Okay, so it's going to be 52 minus 8. Not 8x, sorry, 8 times by 6. Because this will always be constant as you make cuts on the top side of the frame. Now, let's think about this 8 kilonewtons now, this 8 kilonewtons here. Now, this will change depending on how much X changes. So, this is basically going to make it go, this is also going to make it go clockwise, if I'm not mistaken. Yeah, so it's going to also make it clockwise. However, unlike this 8 kilonewtons here, it will depend on X, so it's going to be minus 8x. However, you have this uniform load, which now you have to consider. Now this is making it go anti-clockwise. So that means, similar to the 52 kilonewtons, is also going to be positive. So it's going to be plus, the uniform load is 2 kilonewtons per meter, so it's going to be 2x, yep, and times the distance away from B, so it's going to be half of x, so it's going to be times by x over 2. So that's going to be 52 minus 8 times by 6, which is going to be minus 48, minus 8x. And it's going to be plus x squared. That gets simplified into x squared minus 8x plus 4. So we have another equation. So we're almost done for this part. So now we're going to be concentrating on this part of the beam. This can actually be done 2 ways, and I'll go with the way I'm going with at the moment, so I don't confuse you. So similarly to what we did in this section, we'll just kind of continue. x here. Make sure the moment's going clockwise or anti-clockwise if you said anti-clockwise, if you've been consistent with anti-clockwise all the time. But since I've been doing clockwise, I will keep it clockwise. Okay, M, uniform load, 2 billion meter. We have 8 kilonewtons. Apologies for the bad handwriting, but you should be able to understand. So let's call this a new point C. So some of the moments about C is equal to 0. Yep. So let's think about this. So this two, let's go with this slightly difficult one first. So M, so we're trying to find another equation for M. So M is going to be equal to this 8 kilonewtons. Yep, it's going to be 8 kilonewtons times by 6 minus x, because you want to find out this distance, because it's acting away this distance away from M. So you want to find out that distance, hence why it's like that. That's the only slightly difficult one. So it's going to be minus 8. Let's see, let's write that down. See, it means 6 minus x. Yep. And that 52 kilonewtons, since it's anti-clockwise, like I said before, it's going to be positive here. 52. It's going to be minus this 8 kilonewtons here will always be acting a distance of 4 meters. So this is 4 meters, and that will be consistent as x gets bigger. So this is going to simply be 52 minus 8 times by 4. Similar to 2 kilonewtons, as x gets bigger, the moment will still be the same at point C. So this is going to make it go anti-clockwise, so it's going to be positive in this sense. So it's going to be plus 2 times 4 times 2, because, you know, half of 4 is 2, so that's where it's acting. So if you simplify that, I'm not going to be long with this, so I'm just going to write what the actual answer is, 8x minus 4. Yep. So at the end of this, we've got 3 equations. So we've got this equation, we've got this equation, and we have this equation. And basically now we can draw the bending moment diagram. However, I said for this part, there's 2 ways of approaching it. You could have done it from this side, or so we've done it from here, and then we've gone here, and then we've gone here. However, there's no reason why you can't do it the other way around. So we could have started from here, and then went there, and then went there. It would still be the same. So let's do that, and just so we can validify it. So this next step will just be proving that we get the same answer, the same thing as basically this. Just so you can, because this bit is a bit long, because we have to consider everything previous to it. So I'm going to have to get some new space. So let's go here. So let's just do this. From x here, and we have, if you remember here, we have an 8 kilonewton load here, and the moment still be positive, should still be acting clockwise here. So M is simply going to be given the equation 8 x, and that makes sense because basically at this point here, the bending moment has to be equal to 0 because there's no support here. So it's going to be allowed to deflect as much as it likes. Well, not as much as it likes, but there's no support kind of doing anything about it. It's acting like a bit like a cantilever. So that means the bending moment at the end of the beam is going to be equal to 0. So if you put 0 into this equation, the bending moment is going to be equal to 0. And then it's going to keep going upwards. So it's going to be 8x, it's going to keep going upwards. So that's how these two equations matches, because this equation here would be going from here downwards, and this one is just going to go from downwards to upwards. So if you was to plug it in, 8 times 1.5, so 1.5 is this length here, Yep, so if I put 1.5 in both the equations, I'll get the same answer. So 8 times by 1.5 gives you 12. So 8 times by 1.5 equals 12. And if you was to put it in this equation, so that would give you the value, that would give you the value at the top part of the beam. However, if I wanted the top part of the beam for this equation, I would have to put 0 into it, and I get minus 12. Which makes sense. Actually, I just realized this is going to be yeah, that makes sense. So now let's actually get to the drawing point of it. So the first equation we had was 52 minus 8x. So you basically kind of have to make an not assumption, but it's kind of like taking which way is positive and which way is negative. So I'm going to see positive as the outer parts of the frame. So all the bending moments that's acting here is going to be positive, and any of the bending moment that's happening inside the frame here, I'm going to consider negative, just so everything is consistent. So in the bottom part, if I put 0 into this equation, I get 52, and since 52 is positive, it's going to be acting in this part. And if I put 6 into this equation, I will get the bending moment at this point. Now since it's linear, I know it's just going to be going diagonally. So 52 minus 8 times by 6, which is the length of this part of the frame, is going to give me a value of 4. No, that was a really bad line. Yeah. So it's going to be 4 kilonewtons. Let's go 52. Well, kilonewtons mean. Now, at this corner, the bending moment must continue. It will never be something like this. 4 kilonewtons here. If it occurs outwardly, then this will occur. This will also be 4 kilonewtons meter. It needs to continue. There can't be any discontinuities. So let's say if it was something like this, and you had the bending. If you had it the other way around, you had it so you had it the other way around, and you had something like this, then it would also be inwards. So the next equation would be applying from here onwards, maybe going something like this or whatever. So consistency is very key here. So since I'm making it outwards, then this one will also be outwards. This 4 kilonewtons. I'm just writing here. So the next equation for this part of the frame is going to be x squared minus 8x plus 4. Now, to make sure if it is right, I can put 0 into this equation, and basically I get a value of 4, and that also matches this 4 kilometers meter. So I know I'm kind of on the right path and getting the right answer with this question. Now if I want to find out, since this is a quadratic, it's a bit more difficult to show, to see the behavior of this beam, and I don't want it to, I don't know if it's going to be doing something like this, or it's going to be doing something like this. So one way I can just find out, you can kind of guess this in the exam, but I wouldn't if I was you, and just so you can be sure, is I would differentiate this. So I'll get 2x minus 8, and I'll basically find at the maximum point. So the maximum point would be when I equal this to 0, and x is going to be 4 when the maximum point occurs. So quadratic, so it could be this maximum point, it could be this maximum point, but since we're going for a positive one and not a negative one, this is the one that we're going to be using. And it just so happens that the length of this beam is, the length of this side is 4 meters, so that means the maximum occurs at the end of the beam, so it's going to be something like this. Yep, that's not a nice curve, don't animate that a bit nicer than should, but yeah, so you have something like this. And this is going to be, if I put the value of 4 into it, I get a value. I'm just using my calculator. So it should be 4 squared minus 8 times by 4 plus 4. So I get a value of minus 12, which makes sense. So minus 12 kilometers meter. Now let's start with the last equation. So the last equation was 8x minus 12. Now makes sense, if I put 0 into the equation, I get minus 12, so makes a lot of sense. And since it's the inside of the frame, I must also start from the inside of the frame. Now if I just put 1.5 into it, it's going to be 8 times by 1.5 minus 12, which gives you a value of 0. So you know the bending moment at the end of any beam is equal to 0, so it's going to be the same thing. So this point is also minus 12 kilometers. It helps to kind of do this for some reason. Just indicate where your moment, where your bending moment is acting. I think it's just convention. Okay. Now remember how I said that if you was to just do, let me see, I think I worked it out. So that's the final bending moment. But remember when I was saying something like this, I had 8 kilonewtons here, and I have a moment here, and I will do some of the moments are, let's leave it. So m would be equal to 8 kilonewtons meter. Oops. AX. Now I just realized that if I do this, then I would have got something like this instead, which would have been wrong. Now the reason why is because you're now considering the frame from like another angle, so you get the same kind of values that you would get. The equations would be the same, however it'd be a positive and negative thing. I haven't tested this out too much, but I'm assuming that it will always be the opposite of what you would be given. However, you can see why this method is quite useful, because you can simply just do this, make it negative. I'm not saying it's completely correct, because I haven't tried it out tried it out that much, but it's very fast, so it'll be useful. It might be useful in terms of the exam, and it does give a similar equation. So yeah, just be wary of this. Maybe try a few examples with this method out. So yeah, this should end this part of the video. But I might do another frame question, possibly with pin, but yeah, that's it. And just to clarify that this is correct, I modeled this on GSA, and GSA gives the same kind of answer. So 52 kilonewtons here, 4 kilonewtons, 4 kilonewtons, minus 12 is a load of 8 kilonewtons to minus 2 kilonewtons here. You could even see the coordinates. They match to what you have for the exam. So yeah, so this is correct. Yeah, so I might do another question in another video, but yeah, that's it.